Okay, now we have the second example here. It's pretty similar to the first example of the Street Fighter game, but now we have tennis match scheduling here. So the objective now of this model, we want to predict whether a tennis match will be played or is played based on the weather condition. There are four factors of weather, which we have outlook, temperature, humidity, and wind. So this will be the four observable variables, the four inputs: outlook, temperature, humidity, wind, and the output, the one that we are going to estimate, is the tennis match, whether it is played or not. Okay. We have collected 14 historical data with all of the four weather conditions and the class, whether the tennis match is played or not. So for instance, in the first data set, when the outlook is sunny, the temperature is hot, the humidity is high, and the wind is weak. In the past, there is an evidence that the tennis match is not played. So we have this kind of data, 14 data, that correlate the four weather condition: outlook, temperature, humidity, wind as the observable variables, and then the variable to be estimated whether the tennis match is played or not. Okay, so based on that table, I derived the probability tables, same like what we did in the Street Fighter game here. So I have 1, 2, 3, 4, 5 tables. The first four tables indicate the target classes. There are two classes there, yes and no. Yes means the tennis match is played. No refers to when the tennis match is not played. So as you can see here, the first table here indicate the probability whether the tennis match is played or not based on the outlook condition. There are three variables of outlook: sunny, overcast, and rain. And then the second table, same thing, but this is based on the temperature. There are three variables for temperature: hot, mild, and cold. And then the third table, we have it for humidity. There are only two variables, high and normal. And for wind, there are only two, strong and weak. And the last table here, just to tabulate the probability of the tennis match, whether it is played or not, indicated by yes and no there. Okay, so now in the objective of this modeling, now we want to estimate or we want to predict whether the tennis match will be played or not, given that the weather, the outlook is overcast, the temperature is hot, the humidity is high, and the wind is strong. So we have these four variables of this weather: overcast, hot, high, strong. And if we refer to the previous table, we don't have that, okay, in here. So we cannot make an estimation of the whether the tennis match is played or not based on the existing table. So we are going to estimate this class based on the Bayesian theorem. Let's take a look again on this table, on this probability table, and then we will calculate the probability of yes, meaning the tennis match is played, given the underlying weather condition X: overcast, hot, high, and strong. And then I will calculate the same thing for no for the probability of no given of X. So let's do it for the first one, the probability of yes given X, where X is again overcast, hot, high, strong. So how to calculate this? Using the chain rule, I calculate first the probability of overcast given it is yes. So let's take a look on the first table. If it is yes and if it is overcast, the probability is 4/9. And then the probability of hot given it is yes, yes, and then it is hot, so it's 0. I put it 0 here. Probability of high, the humidity is high, given it is yes, it will be 3/9. I put it here. And then the probability of the wind to be strong, given it is yes, it's also 3/9. Okay, and then the last one I multiplied with the probability of yes, probability of the tennis match to be played, which is 9/14. And if we multiply all of these values, we get 0, because the second variable is 0. The probability of the temperature is hot given the tennis match is played is 0 here. So the probability of yes given X is 0. Now I do the next one for the probability of no given it is X. So I exactly do the same thing. The first variable here, probability of overcast given it is no, is 0. So I put 0 here, and then I calculate the rest. Probability of hot given no, high given no, strong given no, and probability of no. Because the first variable is 0, then the probability of no given no given X, probability of no given X is also 0. Both of them are 0. So what will be the conclusion there? Both of them are similarly 0. We don't have a conclusion. To overcome this problem, we use what we call as a Laplace smoothing. So in this Laplace smoothing, basically I add 1 to all the occurrence here. So if you refer to the table, the frequency table, I didn't pop it up before. So if you, the original frequency table, this will be 243 based on the historical data, and this will be 302063. This will be the original frequency table, and so on and so forth. In order to avoid the 0 problem, I add a value of 1 to all frequencies. So I add these 2, I add it with 1. 4, I add it with 1. Even when we have 0, I add it with 1. So I do this to all of the values in these tables. In such, at the end, I don't have any single element with 0 value. And of course, the consequence, the total class for yes will be 9 plus 1, 10. For no will be 5 plus 1, it's equal to 6. So the total number of classes will be, the probability of classes will be slightly added up now. But in short, I don't have 0 element in here. Treating this frequency table same like before, I can derive the probability table with the new frequency values. So these will be the new probability tables that I use. And then I will use this probability table again to calculate the probability of the tennis match being played or not. Same like before, but now I use the new probability table. I calculate the probability of yes given x and probability of no given x. So from this table, I use all of the values here, and then I calculate the probabilities of whether the tennis match is played or not given the observable variable x there. You can try it by yourself to calculate this, and then but then in short we conclude that the probability of no given of x is the largest now here. So from here we can easily predict that there is no tennis match to be played. Okay, so this is one technique to mitigate the zero probability problem. We use what we call as a Laplace smoothing